Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Nur Amirulhaq Binti Yusof. My thermometer is AD170056, and today I will like to present about effect of reaction temperature and inlet velocity of a bubble column reactor on the bubble size for biodiesel production. First of all, I would like to thank to my supervisor, Dr. Nurul Fiitriah Binti Nasir, who will help and guide me in this project. So today for my presentation, I will present about the introduction, literature review, methodology, analysis of my project, and conclusion. So we go to the introduction. Okay, for background of study, the study of the production of biodiesel, which the process of reacting the triglyceride with an alcohol to produce the fatty acid methyl ester by transesterification process. We can see on the figure 1 show the chemical reaction of the transesterification reaction process. Next, the transesterification process mostly occur in the bubble column reactor, which because the bubble column reactor is more efficient and undergo in a high temperature and pressure. Next, the bubble produced in the bubble column reactor during the transesterification reaction for biodiesel production. Lastly, the study being conducted to determine the effect of the various reaction temperature and inlet velocity on the bubble size in the bubble column reactor. Problem statement. So, the size of bubble will produce in the bubble column reactor during the transesterification reaction, which will affect the productivity of the biodiesel production. Thus, the various reaction temperature and inlet velocity used to determine the size of bubble produced in the bubble column reactor, either it will increase or decrease the productivity of biodiesel production. Next, we will continue to the objective, which the objective of this study is to identify the effect of various reaction temperature and inlet velocity on the bubble size in the bubble column reactor for transesterification reaction. The second objective is to conduct a simulation of biodiesel production in the bubble column reactor by using various temperature and inlet velocity. The last one is to investigate the bubble size produced for two types of perforated plate used in the bubble column reactor. Next, we go to scope of the study. The first scope is the computational fluid dynamics, which is called CFD simulation, is conducted is to identify the effect of various reaction temperature and inlet velocity on the bubble size in the bubble column reactor for transesterification reaction. The second scope is the inlet velocity of the bubble column reactor is at 2 meter per second to 6 meter per second, and the temperature for the reaction ranging from 523 Kelvin to 563 Kelvin. And next, the scope of our study is the bubble column reactor has two models with different type of perforated plate, which are a round and hexagon plate. The last scope of our study is the model were designed in the SolidWorks 2018 and be imported into ANSYS Flume software. Next, we continue about literature review. The first one is transesterification reaction in bubble column reactor for biodiesel production. The transesterification reaction occur in the bubble column reactor will produce bubble which be heated in high temperature. Based on the experiment by Giuliani et al., the bubble produced in the bubble column reactor which is generated by blowing superheated methanol. And next, the increase of productivity of the biodiesel when the temperature rating is increased. It can see in the figure 2, which show the result of the mass of product change on the various temperature since the increase of the reaction time and the temperature, the increase of the mass of the product. Next, effect of various temperature on the bubble size. The number of bubbles produced in the bubble column reactor can be determined by measuring the vapor volume fraction, which is represent the bubble. We can see on the figure 3 show the result of vapor volume fraction in CFD simulation at 523 Kelvin, 543 Kelvin, and 563 Kelvin by Suhaimi and Nasir 2017. And It also states that the increasing of the bubble rising velocity, the decrease of the gas holdup, which will produce the largest size of bubble. Next, the effect of various inlet velocity on the bubble size. The increasing the inlet velocity, then the gas holdup will increase. Therefore, the gas holdup is affected by inlet velocity. The size of the bubble will affected too. So, the increasing of the gas holdup will produce a small bubble size. And we can see on the figure 4, the gas holdup versus flow time with different inlet velocity by Saiful-Bahri 2015 show that the increasing of the gas holdup with the increasing of the inlet velocity. Next, we continue to methodology. So this my flowchart of my final year project, show our progress project until we can define the conclusion. The CFD modeling process. There are three major steps of the CFD modeling process, which are pre-processing, processing, and post-processing. Which in pre-processing stage, the geometry of CFD region was construct and computational machine generate in ANSYS Fluid. For processing, the physical model, boundary condition, initial condition, and other appropriate parameters were defined model step and solving. Finally, the result could be obtained throughout the computational domain in the post-processing stage. Next, we continue for phase of design. The first step is modeling, which SolidWorks software will use to model the bubble column reactor with different type of obstacle of perforated plate used. We can see on the figure show the design A of the perforated plate and design B of perforated plate. Then the next step is a transfer, which we import the model directly from SolidWorks to ANSYS software. The last step is the simulation, which we run the simulation to determine the behavior of the fluid flow using fluid on ANSYS software. Next, assign fluid domain and name selection. There are three name selection for fluid domain: inlet, outlet, and boundary wall, which can see on the figure show. Next, we go to meshing. For the machine, in meshing process, the phase sizing is controlled at 5 locations, include perforated plate in the bubble column reactor, which to produce the best skewness, which affect the calculation in the solution. Next, the meshing setting has been changed in order to provide a better and smooth iteration in the meshing process. And we go to the processing solver. These are solver that we use for the simulation. Next, we go to the analysis of my project. For grid independent test, GIT, the best GIT of the mesh is referring to the skewness and orthogonal quality of the mesh, which can be determined based on the mesh matrix spectrum. GIT with 156669 number of nodes was selected to be the best mesh setup for design A because the skewness of this mesh obtained is the lowest. Hence, the mesh of this node is good mesh and orthogonal quality is excellent according to the mesh matrix. On the GIT of 147377 node was selected for design B as the best mesh setup because the skewness of the mesh is the lowest and accepted from other nodes. The orthogonal quality of this node also in excellent condition. For the gas holdup, the value of gas holdup was defined as the volume fraction of methanol gas in the total volume mixture from the simulation, and the value of gas holdup increased when the increasing of the velocity and temperature in the reactor. According to Tao et al., the result of the experiment and the simulation obtained show that the value of the gas holdup for the largest bubble size occur in the bubble column reactor will not exceed 0.3, and the large bubble size contain higher velocity and the lowest gas holdup based on the Suhaimi and Nasir. Next, for gas holdup for design A, the graph show the gas holdup versus flow time for 5 to 3 Kelvin. The trend show the value of the gas holdup was increased as the inlet velocity was increased. The increase of the velocity will give the increasing the value of the gas holdup, which could affect the bubble size in the bubble column reactor. The small bubble size produced in the bubble column reactor for 5 to 3 Kelvin is the less bubble size. Next we go gas holdup versus flow time for 3 Kelvin. And the value of the gas holdup show in the graph start to increasing when the temperature used in the 540 Kelvin. The value of the gas holdup for 6 meter per second show the higher value than other velocity. Next we go to the gas holdup versus flow time for 563 Kelvin. So based on the graph, the value of the gas holdup for 563 Kelvin for each velocity is higher compared with 523 Kelvin and 543 Kelvin. And the higher value of the gas holdup in 563 Kelvin by increasing the velocity in design A was at 6 meter per second, which provide 0.598 at 2 seconds. The bubble produced for 563 Kelvin at 6 meter per second is a small bubble size. For gas holdup for design B, the figure 9 shows the gas holdup versus inlet velocity for design B. The value of the gas holdup shows the same value on the location, which be set in the bubble column reactor. Therefore, the value of the gas holdup was plotted for 1 point for each temperature and inlet velocity. The highest value of the gas holdup obtained from the graph for design B was at 563 Kelvin, which was provided 0.450 at 6 meter per second. The value of the gas holdup in design B is lower than the gas holdup for 523 Kelvin and 543 Kelvin in design A. Next, volume fraction of methanol vapor. The volume fraction of methanol vapor show the behavior of the methanol gas dispersed in the bubble column reactor based on the temperature and velocity used in the simulation. Next, the diameter of the bubble was defined from the change of the value of gas holdup, which the volume fraction of methanol will determine the value of gas holdup in the reactor. Based on the figure 10 and 11 show the volume fraction of the 563 Kelvin at 2, 4 and 6 meter per second for design A and design B. For the velocity vector show the circulation of the flow pattern of the mixture of fluid from the inlet through the outlet of the reactor. Next, bubble interaction in the middle in the reactor, which in the form of homogeneous, will produce stability of the bubble rising within the liquid, which can cause the increasing of the gas holdup. The velocity vector at 563 Kelvin show higher at outlet of the bubble column reactor than 523 Kelvin and 543 Kelvin for design A and B. The figure 12 and figure 13 show the velocity vector for design A and design B. Next, we go to the velocity streamline, which the streamline for the mixture of the liquid has been generated from inlet to outlet by pass through the perforated plate, which in the lower part of the bubble column reactor. The liquid will move around the lower part of the reactor because it passed through the perforated plate. The streamline show for the design A and B are same for each temperature and the inlet velocity in the bubble column reactor. Next, effect of the temperature on the bubble size. The reaction temperature is also important in affecting the gas holdup in the bubble column reactor. We can see on the graph in the figure 4.16, we show the increasing of the temperature will increase the gas holdup. And the increasing of the temperature produce the small bubble size, which by increasing the gas holdup, while the decreasing temperature will produce a large bubble in the bubble column reactor. Next, we go to the conclusion. In conclusion, the identity of the bubble size in the simulation was obtained based on the value of gas holdup in the reactor. The increasing of the temperature and inlet velocity in the simulation produced the increasing value of the gas holdup. Therefore, the higher value of the gas holdup produced the small bubble size in the reactor, while the largest bubble size occur when the decreasing of the value of the gas holdup. Next, the value of the gas holdup show for the design A increasing since the temperature and inlet velocity increase, while the value of the gas holdup obtained from design B show the same value for the whole flow time. Next, for the recommendation, I would like to propose a better design of perforated plate to be used in the bubble column reactor, such as install another type of obstacle with a different shape that can give efficient result. Next, to propose the alternative fluid used in the reaction of the mixture in the bubble column reactor to obtain more accurate and efficient data. The last one is use a very high specification computer to run the analysis simulation in order to reduce the required time to simulate the large scale model geometry. That's all from me. Thank you.